The next model of computation is Turing machine. So this machine has got an infinite input tape, very similar to finite automaton and push down automaton, and there is a control unit which can perform both read as well as write, which means on reading a symbol it can replace that by some other symbol. Write operation is allowed. If you look at finite automaton, it is an infinite tape with uh, just read operation. And if you look at PDA, it is same. In addition to that, you have something called stack. If at all write happens, it is on this. It performs push and pop. Now this one is superior to these two, and in which one can read a symbol, say the input tape contains AB, AA, let's assume end of the tape is dollar. Then after reading this, you can replace that by something like this. Then you move right and read this, and then you do nothing. Then again you move right and read this. The interesting part over here is, if you look at finite automaton and push down automaton, it can only move right, there is no left move. For both, there is no left move. So whereas Turing machine can move in either direction. As far as movements are concerned, it can move both left as well as right. Except the first symbol, for all other symbol, you are allowed to have both left as well as right. For the first symbol, it is only right. So which means after reading this, I may change this to say X, then move left, and then read B and take some other call. Fine. But it cannot jump. It cannot jump from here to this in one move. But of course, if jump has got k cells, it can move one cell at a time until it reaches this position. Fine. But there is no direct jump from one location to another location. It is always one cell movement. It can move both on the left direction as well as on the right direction. Now the question is this: by adding this additional power like stack, we were able to see that a power n, b power n was recognized by push down automaton, which was not recognized by finite automaton. Now language like a power n, b power n, c power n, there is no CFG, there is no PDA, no PDA can recognize. Now the question is, can this additional power or can this machine recognize languages of this type? Okay. So now with this you come to know that the limitations of PDA are something that PDA cannot solve, Turing machines can solve. Now with this we ask, we solve a couple of questions and then we understand the computing power of Turing machine. Subsequently we ask what is the computing power of Turing machine and what is that it can compute, what is that it cannot. Okay. And then what more one should add to increase the computing power of Turing machine. And in the process we slowly get to modern day computers. And we ask how close is it to modern day computers. And if you are interested in modeling modern day computers, or if you are interested in understanding the computing power of modern day computers, which model I should go for? Should I work with FA or should I work with PDA or should I work with Turing machine? Is Turing machine all powerful? And whatever you could do with modern day computers, you can do with Turing machine. Okay, so all such questions we shall explore. To start with, let's construct Turing machine for a power n, b power n, c power n, so that you understand the configuration, the movements, and all that. Okay, here is the logic. Suppose the input is a, b, b, c, c. Now we need to check this, and this. They're all of same size. Equivalently, for each A, I should look for corresponding B and corresponding C. So when I read this, I should look for a B, I should look for a C. So every time, if that is guaranteed, then at the end we can say that given string is of the form a power n, b power n, c power n. Okay. Remember, there is no separate tape or a stack where you can write. You can write when you read a symbol at that place itself, or maybe you can move right and then somewhere on the other side of the tape you can write. What am I saying? You have an input tape. In case you want to replace this symbol by something else, that write is allowed. Or you want to remember that you have read A. Maybe you can move right by a couple of cells, and somewhere here you can write capital A. Then come back and then read the next symbol. So there is no separate storage like stack as we add in push down automaton, but that feature can be simulated here. What am I saying? Whatever you could do with this stack, same thing you can do it here. Somewhere down, you allocate a space for stack or a storage, and wherein you can store and then come back and read the subsequent input. Fine. So with this framework, let's design a mission. So here is the logic. When I read this small a, I'll change this to something like say capital A. Then for this I should look for corresponding B and corresponding C. What I do, I move right. When I encounter this, I'll change it to capital B. So some symbol. Okay, this says B has been read. Then we move right and change this to something, say X. Then I change my direction until I see the leftmost A. Or I need to continue this process, which means I need to look for the next little a. So I change this to capital A, and for this I should look for a corresponding B. I'll change this to B, I'll change this to X. Fine. Now this is a valid input, but in the process you may come across things like this. So you may have AA, say triple B, double C. You change this, move right, change this, move right, then you come back, change this to capital A, change this to capital B, then change this to X. You come back and you see that there are no A's. But when you move right, you see that there is one little b. So when you come across such a situation, you have to go to a reject state, which means this is an invalid input. Okay, so things like this can happen, or we may have more A's and less B's. So after two iterations, you will have AA, BB, XX. Then you come back and change this to capital A, and you move right, and thinking that you will see a corresponding B, but there is no corresponding B, which means this is invalid. Okay. On the similar line, we may find more C's, that is invalid. So something like ABCC, you will change initially to this, and then when you come back, when you see that AB is exhausted, you move right. When you move right, you see that there is one C. So when you move right, you see excess C, and then you conclude it as invalid. Okay, so on the similar line, we may start with B, or we may start with C, and all that is invalid. Now, how are we going to describe this mission? Okay, and this mission has got input symbols, and in addition to that, because we replace this by some other symbol like A, B, X, and so on, we need an additional alphabet. Just like we add a stack alphabet called gamma, here also we will have an additional alphabet called gamma, where we will have this A, B, X, and so on. Fine, with that we describe our mission. So let's formally describe the signature and then get into the transition function. Fine. The signature has got the following. We have set of states Q, Q0 to say Qk. Then sigma contains A, B, C, and so on. Then we use additional symbols like A, B, capital X. We use dollar to mark the end of the tape, and so on. Then start state is Q0. Then you have transition function delta. Final state is F. And as far as the direction is concerned, one can move left or right. And after doing some computation, we want to stop the mission. We say halt, which means stop the Turing mission. And once we say halt, there is no further transition, no further read write, and no more transitions. Okay, so it cannot read further, it cannot write further, it cannot move further. It simply stops the mission. And with that, you conclude what is that this mission can accept, and so on. Fine. So remember, you have this input tape. So for this language, suppose you have string like this, you can replace this by A, move right, replace this by B, move right, replace this by X. So when you move, you can only move one cell at a time. You cannot jump. So which means, supposing the input is like this, so after reading this, you replace this by capital A. Then one has to linearly scan one cell at a time until we encounter little b. Okay, so there is no jump from this to this b. Similarly, after replacing this by capital B, one has to linearly scan one cell at a time until we hit this C. There is no jump from this to this. Okay. So in case you want to remember something, write something somewhere else, what you can do is, we usually have something called dollar, which will represent the end of the input. What you can do, you can keep this as your working tape or input tape. To the right of dollar, you can use it for additional storage. You can move right after dollar in case you want to write something like capital A, you can write and then you can come back and proceed with the next iteration. Okay, so it's a framework. We come up with appropriate notations, and with this notation we describe this is how the machine works. And this additional storage, you can read from left to right, you can also read from right to left, meaning you can see them as queue, you can see them as stack. In whatever way you want to read, access, it is permitted. Okay, so now let's describe the formal way of seeing how a power n, b power n, c power n is recognized by Turing machine. One can come up with a transition diagram, one can come up with a transition function, one can also come up with a grammar. So all that we shall see in due course. Okay, now let's look at the transition function for a power n, b power n. The logic that we are going to implement is the following. Replace a by capital A, move right, and replace the corresponding b by capital B, move right, replace the corresponding c by x. Come back and continue this process. Look for the next a and then followed by b, followed by c, continue this process. At some point in time, you come across an invalid input. Some of them we have already highlighted. You conclude it is invalid, and you enter a reject state, and the moment you enter a reject state, you say it is invalid. But for both reject state and final state, you must stop the mission. So for all valid inputs, the Turing machine must reach a final state followed by stop, and for all invalid inputs, Turing machine must reach some reject state. Most importantly, it must stop. Okay, the mission must be stopped irrespective of whether it is in final state or reject state. Over here it is rejecting and stopping the mission. Over here it is accepting and stopping the mission. Fine. Let's get into the design.